Hi everyone, so my name's Andrew and welcome to your first video with me. So I am a postdoc here in the School of Maths and Physics, and I am going to be taking you through the second half of this module, tensor field theory. So in chapter 4, which is called Tensor Calculus, and that's what we're going to be starting here, we're going to be going back to the ideas that we saw in chapter 1. Okay, so for the time being, we're going to leave all of the relativity stuff behind, the physicsy stuff, and just go back to the maths of tensors. And then after we've covered that, we will move on to general relativity in chapter 5. So in this first video, what I'm going to do is just a very, very brief recap of the main, most important points that you need to know from chapter 1. And everything I do in these videos, by the way, will be done more fully in the PDF lecture notes on Canvas. But I will use the videos to just draw your attention to the most important things that you need to know from notes. The only thing really that might be different in the videos is that I may do some different examples or some additional information that's just for your interest. But anyway, let's then start with some revision of the main things that we need to know from chapter 1, which was called Tensor Algebra. So we need to know about contravariant vectors and covariant vectors. Okay, so in general, if you have a vector field, so let's just call it capital T, and let's put an underline because it's a vector, you can express a vector field in terms of components multiplied by basis vectors. Okay, components multiplied by basis vectors. But as we saw in chapter 1, you can use the contravariant components along with the natural basis vectors, or you can use the covariant components along with the reciprocal basis vectors. So you can write it this way, so T superscript I times natural basis vector AI, so that's the contravariant form, or you can write the vector in the covariant form, so T subscript I and then basis vector E with a superscript I. That's the reciprocal basis vector. So two ways of writing the same vector. And what do we need to know about these different objects? We need to know the transformation laws. Okay, that's the most important thing really. So for the contravariant components, Ti, if we transform to another coordinate system, so if we put a bar there, the transformation law is as follows. So dx, dx, and then t, a, and then we have an I here, an a here, and a bar here. And as for the corresponding transformation for the covariant components, it looks like this. So t bar subscript I equals dx, dx, t, a, I bar. Okay, so those are the transformation laws for the contravariant vector components and for the covariant vector components. Those you should know off by heart. And then there are also the corresponding transformation laws for the basis vectors, which we don't need so often, but I suppose I can write them down anyway. So remember actually how the basis vectors are defined in the first place. So for the natural basis vector, how is that defined? You take the position of the point in question, okay, so the point where you want to have your basis vector, so point R, and you differentiate with respect to coordinate xi. So that's the natural basis vector, and then the reciprocal basis vector is defined through the following relation. So E superscript I dot product with E subscript j is equal to delta I j. So the reciprocal basis vectors are orthogonal to the natural basis vectors. Okay, and the transformation laws then are as follows. So E bar I is equal to dx, dx, E, A, I bar. And the transformation law for the reciprocal basis vector, E bar I is equal to dx, dx, E, A, I bar. Okay, what else do we need to recall? Yeah, so those are the transformation laws just for vectors. Of course then, as you saw in chapter 1, this generalizes to tensors. So components of a vector have just one index. Okay, so a vector is a rank 1 tensor. For a more general tensor, the transformation law would be as follows. So maybe I can use a different color. So if I have a tensor in general, and its components are t, and then we have, let's say we have p contravariant indices, and let's call them I1, I2, ... IP. And then we have q covariant indices, so let's call them J1, J2, ... JQ. And the transformation law is, so if I put a bar on it, the transformation law is as follows. So we have dx, dx, I1, A1, all the way up to dx, dx, IP, AP, and we put bars on all the upstairs x's, the xi's, and then we have multiplied by dx, dx, J1, B1, all the way up to dx, dx, JQ, BQ, and we put bars down here with the j's, and then that is all times t, A1, A2, ... AP, B1, B2, ... BQ. So that is the transformation law for a general tensor, which looks quite messy, but really it's quite easy to remember if you know these ones. Okay, so if you just remember the transformation law for the vector, this is just a very natural generalization of that. Okay, so for each contravariant index, in other words, for each upstairs index, you get a partial derivative like this one from the contravariant vector transformation law. So the bar is on the top x, and then for each covariant index you get a partial derivative that looks like this one, that comes from the covariant vector transformation law with the bar on the downstairs x. And then at the end of the day it gets multiplied by t with some dummy indices. Okay, so that's all of the transformation laws. The next thing we need to look at then is the metric tensor. Okay, so the metric tensor is a very special rank 2 tensor. So let's write down metric tensor, and most of the time it's denoted by a small g, Gij. Okay, so a rank 2 tensor, and what it does is it allows you a way of measuring distances between points in your space. So in particular, the squared distance between two neighbouring points in the space is given by, so typically we call that squared distance ds squared, and it's given by Gij dxi dxj. And then if we want to find the distance between 2 points along a certain curve, so say we want the distance between point A and point B going along the curve, which we will call C for curve. So in other words, we have a point like this, so point A, a point like this, point B, and we go along some path, C. So the metric tensor gives us a way of finding the length of that curve C, and it's as follows. So we call the length S, and it's given by the integral of ds along that curve, okay, between point A and point B. And ds can be found from here. Okay, so this is the squared distance, ds squared, so we just take the square root of that. So it's just the integral along the curve of the square root of Gij dxi dxj. Okay, but how do we find an integral like that in practice? The curve is parametrized. Okay, so we parameterize this curve. So if you have a point, imagine you have a point on the curve, just an arbitrary point on the curve with coordinates xi. We can parameterize the curve by a variable. Let's just call it u, so just a scalar. So xi is equal to xi of u. In other words, the coordinates are functions of some parameter u. So if we do that, that gives us a way of turning this strange looking integral into just a more familiar one-dimensional integral. As follows, and we do it using the chain rule. So this becomes an integral from the value of u at point A to the value of u at point B, square root gij, and then using the chain rule, basically, we can write dxi by du, dxj by du, and then outside we can put another du. So that gives us a way of finding the length of the curve between point A and point B. The very last thing to note about the metric tensor is that it can be used to raise and lower indices. So for example, if I have, let's say, a covariant vector, tj, and then I multiply it by gij superscript, then this gives me the contravariant vector, ti. And similarly, if I do it the other way, so if I start with a contravariant vector, tj, and I multiply by gij subscripts, then this gives me ti, the covariant vector. And by the way, I should point out, so the metric tensor with superscripts, so the contravariant metric tensor is the inverse of the covariant metric tensor. Okay, so remember, this is a rank 2 tensor, the metric tensor, so it can be written as a matrix. So what I am saying is that the covariant gij, so this one, is the matrix inverse of the contravariant gij. In other words, if I have gik, gkj, this is nothing other than delta ji. And I should also say as well, the metric tensor is symmetric in both forms. So remember that gij is just the same as gji.